Endiatx is a journey. It's 3 words put together. It is to go inside the human body. It is to understand what is wrong, and it's to fix it. And so, to put that very simply, we are putting tiny robots inside the human body. But let's go back in time for a moment and look at the ways that we used to go inside the human body to find disease and to cure it. There are amazing records of ancient Egyptians doing brain surgery. And so these traditions of very elegant and intense healthcare are not just recent inventions. But recently we have decided to ask ourselves, are there ways to do it with less invasiveness? I think that with laparoscopic surgery, we had huge breakthroughs where you could just poke a hole and slide a tube, so to speak. However, actually, imagine if you could just take the tip of one of those devices and subtract the device. Imagine the tip of the endoscope doing its job, or the tip of the catheter minus the catheter. And this is where we actually need to turn to the world of science fiction for a little bit of inspiration. So we believe that micro-robotics inside the human body can help serve as a platform for a new type of medicine. So let's say a big word. In the US, we like supercalifragilisticexpialidocious. That's a Disney word. But I give you esophagogastroduodenoscopy. And this is what we do when we want to look inside your stomach. And it's funny, we might only want to look inside you for 5 minutes if you've had some kind of GI ailment. But oh my goodness, look at all the equipment that's necessary to make this happen. This patient might be going to the hospital multiple times before they get a procedure like this. And you can see that modern healthcare, imagine the healthcare industrial complex with all of its power and all of its might, it comes with a heavy footprint. And so what we are trying to do here today is ask ourselves, can we take much of what we do in a modern hospital and digitize it, dematerialize it, turn it into telemedicine from home? And with AI, I believe that asynchronous telemedicine can really scale this to everyone on the planet. And so with that, I would like to hand this over to Tomas to take the dream and turn it into a reality.
With the goal of microrobotics as the next step in medicine, we gave ourselves the challenge to build a wireless robot capable of navigating inside the human body under its own power while transmitting live video in real time. So building small robots is very difficult. So we started off quite large with PillBot. This is a wireless robot capable of swimming around, as you can guess, a swimming pool. And the real challenge was, how do we go from this football-sized device down to the 13 by 30 millimeter robot we have today? And SolidWorks really played a key role in this 90% reduction in size. And so in order to successfully navigate and visualize the stomach, there are some key components that make it possible. We have a lithium-ion battery with a high C rating that not only powers the electronics, but also can handle the high spikes in energy needed to power the motors. We have LEDs, or light-emitting diodes, in the front because the stomach is a very dark environment, so we have to bring our own light inside. If we take a closer look at the back of the robot, we call this the tail cone, we can kind of see the intricate geometries that allow for three-dimensional flight. Taking a look inside, we see complex systems of motors, propellers, stators, and lumens that allow us to keep a compact form factor while not compromising on functionality. So the stators are the two components in the back, and there's one on the top and the bottom that we can't see here that direct the flow as it exits the lumens, the tubes through which the water flows. And at these scales, we're dealing with low Reynolds numbers. This means that water starts to behave more like honey rather than your typical low viscosity liquid. And this becomes very unintuitive. And this is where tools like SolidWorks flow simulation really are key. They give, given the infinite possible combinations of propellers, lumens, and stator geometries and the relative position, having a tool like this to quickly iterate and visualize the flow is really important. And so here we have some screen captures. The arrows represent the direction of the flow, and the color represents the speed, red being fast and blue being slow. On the first one, we see some turbulent flow behind the propeller, which creates an unoptimal flow at the outlet. And then we change the geometries and the relative position of the components, and then we can see that we have more of a laminar flow at the bottom right corner, with much higher flow. And now Kevin will give us a closer look at some of the challenges our electrical engineers had to face.
So let's look at some of the electrical key challenges we have today. The first thing we have to look at is size. As you saw previously on the other slide, the robot was eventually, or at some point, very big. We had to make it very small. But how do we put all the electrical circuitry inside the robot? So what you can see here on this slide on the left-hand side is a rigid flex circuit board in a flat pattern. We then basically have to use origami to fold and bend it to the picture on the right-hand side. Once it's in that form, we're able to put it into its capsule. Now, I have to work very closely with Thomas here because we have to make sure that there's no part interferences of any kind. And this would not be possible without SOLIDWORKS. The next electrical key challenge I want to talk about is capturing high-resolution images. So our rigid flex circuit board is very similar to the human visual system. We basically need light to see, and in order to capture an image, we have a high-resolution camera, which is basically your eye. We then have to send that electrical data, just like nerves do to your brain, to what we like to call an FPGA, which is a field programmable gate array. This would be considered the visual cortex of the brain. This is where all the image processing happens. After this data is processed, we then send it to an integrated circuit called a microprocessor, which manipulates the data and sends the data out wirelessly through a custom tuned loop 915 megahertz antenna. Now let's talk about one of the final electrical key challenges for today, which is radio frequency. So one of the steps that we have to do in order to take the PillBot is we have to drink some water. So now imagine that you're the robot inside the human stomach, and we want to get that radio frequency signal outside the human body. Those radio waves have to travel through water, organs, skin, air, and then finally it reaches a computer where the data is received wirelessly. One concept I want to share with you guys today is a lot of people actually think radio waves travel in one direction, but they actually travel in a spherical manner. And so with that said, I want to show you some data that we've obtained from an RF chamber in Silicon Valley. So what you can see here are 3D gain plots, where gain is the ratio between the input and output of the antenna signal. Red means higher gain, the red color, and like the lighter colors is basically lower gain. There's pictures of PillBot there in different orientations, so you can see how there's more powerful direction in some directions, right? And so when the robot's inside the human body, based upon where the robot's moving, it basically will give us different results. And this is one of our biggest challenges today. And we basically have to go through a lot of optimization and tuning techniques to optimize this signal. But more to come, and so stay tuned. So with that said, we have to juggle all these challenges and think about all these challenges at the exact same time. And it makes working on this robot very challenging, but fun.
And so now we're going to begin some demos for you guys and kind of show what we have. And so this is this is a tank flight bot, and so we're going to fly this around the tank, and you'll be able to see how it actually performs in real life. And so as you noticed here, Quentin used a light to trigger a photodiode on the front of the bot that turns it on. And then we're going to prime the lumens. And so an important part is to make sure that the lumens, the tubes in the back, are filled with water. If a bubble gets stuck, this leads to poor performance. As we know, robots and technology hates to perform on stage. So let's give Quentin a second to
One
connect
thing
everything.
we're extremely proud of is the neutral buoyancy that you see there. by tuning the robot's volume and its weight very carefully to mimic a water density, we get to minimize the amount of mechanical force necessary to swim around. And so we work very hard to get this relatively neutral buoyancy.
Today, we're going to be using an engineering tool. The robot on the left here is called Flower. So this is an unmotorized device that is designed to always point upward and sink to the bottom of the stomach. And so it's the same circuitry, we just kind of ripped out all the motors, and this allows us to see PillBot in its natural environment, right at the stomach. This is a great tool for the engineers to kind of debug any issues that might arise during the swallow process. So before having Flower, we would actually go to a GI facility, and they would perform an endoscopy while we had a PillBot inside the stomach. And that's very, very uncomfortable for Torrey to receive. And so we had to design this tool to kind of help us out with those issues.
So this guy is going to be our cameraman today inside the body. Yeah, let's put this up on screen. Okay, so there's me. And does everyone want to wave and say hi? The neat thing here is you can see a little bit of cloudiness, a little bit of haziness. I actually had a little bit of GI trouble this morning, and it's kind of neat to actually go in and see what was going on. But let's try to get a live video, and Kantan will just tell me when he wants me to go. One of the challenges we have with PillBot is that we need to do all of the video processing on the robot that would normally take place outside of the human body in an endoscope tower, basically on a big computer, with that cable coming out of your body transmitting just that raw data. So we actually have to do a lot of very powerful computation in a very limited compute environment. And that means that the software engineering and the electrical engineering going into PillBot is actually quite sophisticated. Okay, so I'm going to go ahead and swallow this robot.
So Torrey's been prepping his stomach. Unfortunately today with the small issues, it's been a bit different. But typically a patient would skip breakfast and just drink regular small amounts of water throughout the day until the endoscopy. So a traditional EGD procedure.
And yeah, so this is a way to give ourselves situational awareness. Although everything that we're seeing right now is intended to be digitized using onboard inertial sensors and also edge detection coming off of the sensor itself, with the idea that if a drone can fly in a park and be stable and hold its position between some trees with a little bit of wind, well, presumably a drone could also hold its position inside a human stomach and swim around deliberately and hold station. So we're very honored to be able to share a little bit of the R&D process with everyone in this room and beyond. Okay, so this is a live view from the actual swimming robot. And you can imagine we're always interested in improving the various image qualities, the mechanical motion, the reliability of the stack. But coming from Silicon Valley as a small, spunky startup, we're actually incredibly proud to be here today to share this process with everyone. I guess I'd like to transition to what happens after we've made this normal. So let's assume that for 72 million people every year, their upper endoscopy could potentially be done at home via telemedicine. We could even let their doctor be in control of it. And that would be really cool, right? It means you don't have to go to the hospital. You might not have to go through several hospital visits that they feel like gatekeeping to some patients. But really, it's just doing proper medicine with the old school establishment. If we can take 70 million hospital procedures and also the procedures that led up to those and digitize it, that's a great leap forward. But beyond that, we just got some amazing intellectual property for the pill surgeon that comes after PillBot. Obviously, we don't want to be a moving eyeball forever, right? Obviously, we would very much like to have tools and cut polyps, possibly take a sample and do a little bit of analysis on the robot. And eventually, although we are so grateful for the human stomach, where you can drink some water on a stage and put on a little bit of a show, The rest of the tissue and organ systems in the human body are of great interest to us. And so we envision a future for PillBot and its descendants going all the way into what we would call microsurgeon. The microsurgeon would be able to cut its way through layers of tissue, find its way into the human brain. Imagine if you had a brain tumor and you had 6 or 12 of these robots working together as a team for months on end, not just one surgery in a hospital, but like Richard Feynman said, swallow the surgeon and bring that into your body.